All right, now we get to start in on spectroscopy, which is by far my favorite aspect of analytical chemistry. It is also kind of what I did and was interested in terms of research. I always found this to be the most enjoyable, but if you do not share that same enthusiasm and passion that I do for this subject, it's okay. It is a beautiful sunny day out today, which is great because the history of spectroscopy actually kind of starts with studying the sun and light and color. And the term spectroscopy actually comes from the Greek spectros and scopy. And so that's why I've got these little Pac-Man ghosts here in different colors, because spectros literally means ghost and scopy means to observe or watch. And so the history of the term goes back to when people were studying the diffraction of light through prisms. They were looking at the different wavelengths of light that made up sunlight. And what they saw was that in that solar spectrum, rather than being a pure continuum of color, that there were places where there were gaps or blank spots, or there wasn't light of a particular narrow band. And we now know those as the Fraunhofer lines, or we know those as elemental absorptions. So in lab, we did an atomic emission experiment. Atomic absorption is the reverse of that process. So we know what's happening with that now, and it's related to what elements are inside of the star. And they compared that to regular sources of light, like a light bulb, or something like a furnace that was getting really, really hot, that were going to act as radiators that would give off a true continuum of light of all wavelengths. And so the fact that these guys were missing from the solar spectrum, because the sun, is pretty hot, should be acting like a black body radiator, and they saw these missing lines, and these are the ghosts in the spectrum. So when we are doing spectroscopy, we are looking for ghosts, which is kind of cool. So spectroscopy is the analysis of spectra, especially light or mass spectra, to determine properties of their source. In light or optical spectroscopy, the spectrum of a light source is analyzed through a spectroscope to determine the atomic composition of a substance. In astronomy, phenomena such as redshifts can also be analyzed, and we can learn things like how far away a star is by knowing how fast it's moving. In mass spectroscopy, a spectroscope is used to determine the composition of ions or charged molecules in a sample. It's also called spectrography. There's a couple of different terms with some subtly different meanings. A lot of those meanings are going to kind of blur together just out of common use these days. So, I'm going to tell you what the terms are, but sometimes they're pretty interchangeable. The one you do not want to get wrong is calling more than one spectra a spectrums. It's spectra. The plural of spectrum is spectra, not spectrums. But if you call a spectroscope a spectrometer, nobody's going to look at you weird. Or if you call a spectrometer if you call it a spectrometer, you're probably pretty good, right? So spectroscopy is the theoretical approach to the science of studying the interaction between matter and radiated energy. Spectrometry is the practical application of spectroscopy. Spectrometry uses instruments called spectrometers. Spectrophotometry is a method used to measure how much of a chemical substance absorbs light as the beam of light passes through the sample. So spectrophotometry is going to be a quantitative approach, a quantitative technique. Spectrophotometers are the instruments used to quantitatively measure the reflection or transmission properties of a material as a function of wavelength, and they will give you a spectrum as the output. So things you should already know: light is a particle, and it's a wave, and it's a wave, and it's a particle. And its speed in vacuum is fixed, and its speed in other media, not in vacuum, is related to its refractive index, which is related to the dielectric of the media and its permittivity of free space, of course, and we're not going to go into that. But the key is that when you talk about C being a constant, there's always this caveat that 2.9998 times 10 to the 8th meters per second, that is in a vacuum. And it doesn't matter what color of light you are, you're going to go the same speed in a vacuum. But as soon as you go from a vacuum to air, or from air to water, or air to glass, or glass to water, that refractive index of that material has changed, and your speed of light is always going to be slower. The higher the refractive index, the slower the light goes. We have made some really interesting materials and metamaterials, and they can slow light down to a couple of kilometers per second. And so if I can find it, I'll try to dig up the video, but it's really cool. They put a pulse of light into this material, and they film it with a high-speed camera, and it just, you see this light going through and propagating through this chunk of material, and it's, going at a speed where you can record how fast that light is going. But it's all relying on the trick that the speed of light, once you get it out of that vacuum, and there's nothing, in a vacuum, there's nothing to interact with that light, it's going to slow down. Now, why is it slowing down? That's because the very simple view is light's an electromagnetic wave. And now if you put it into a material that has some electrons associated with it, there's going to be some interactions, but it's actually way more complicated than that. We're going to characterize light by its color, right? So red, green, blue. We can characterize it by its wavelength, right? So how many nanometers are there between peaks on a particular wave, and that's going to correspond to color. Energy, to energy, there's some tricky units for energy. We can do it by frequency, with the frequency of the light. Centimeters to the -1 is the frequency unit that we'll see when we do Raman spectroscopy, or if we do infrared, FTIR. So here is our light wave. I'm going to describe a wave. It's going to act like any other wave. It's got a wavelength. So the wavelength is between one peak and one peak, or one valley and one valley, or one node and the corresponding node on the other side. It's got a frequency. So if we got a wavelength, and this thing is propagating through space at a particular rate, so it's going to go at the speed of light. If I've got a velocity and a wavelength, I can count how many of these peaks pass by at a particular time unit, and that'll give me a frequency. And then it's got amplitude. All right, so amplitude is how big this wave is going to be. Light can also act like a particle. So it can act like a photon, or a quanta of light. All right, so it's participating in this whole quantum wave particle duality business. So our wave characteristics include period, that's the time in seconds to pass through a fixed point. Frequencies, the number of oscillations per second, and the units on that are hertz, or seconds to the -1. Sometimes you will see on very old radios, like from the 1950s and stuff. So rather than listing stuff in kilohertz or megahertz, it will have CPS on there, which stands for cycles per second. And it's still the same unit, it's just they're calling it cycles per second instead of calling it hertz. See, this is the point in the class where if we actually had somebody around, I would say, hey, do you guys know what a hertz donut is? And then I would pretend to punch somebody and be like, hertz donut. So C is going to be related to our frequency, nu. So this Greek letter here is a nu, over nu times lambda. And you can rearrange that, and then I can tell my other great joke for the day, which is, hey, one photon walks up to another photon and says, hey, what's nu? And the other photon says, C over lambda. So nu is equal to C over lambda. C is equal to lambda times nu. And C is going to be 3 times 10 to the 8th meters per second in a vacuum. We also have this unit called wave number, and that's going to be 1 over lambda. All right, so wave particle characteristics, E is equal to h nu, so which is saying that the energy of a photon is going to be equal to its frequency times h, and h is just Planck's constant. So our energy is H times C over lambda, or you could do it as H is equal to C times nu bar. Right? And Planck's constant is 6.6 times 10 to the minus 34 joules times seconds. Right? So Einstein's Nobel Prize is not for relativity. A lot of people think it's the whole E equals mc squared business. It is more for this. It's for the photoelectric effect, which shows that light behaves as a particle. So the photoelectric effect would not work if light was acting like a wave. It showed that as you make basically a vacuum tube, and in that vacuum tube you apply a potential across a cathode made of a particular material, and you have a photon coming in, and you see no current being generated until you get to a particular energy of photon. So until you get to a photon that has enough energy of the right color, it's blue enough. Right? Once it gets to that right energy, it's able to smack into that cathode, kick an electron off of it. The electron goes from the cathode to the anode, current starts to flow, and so you can start to generate current through this photoelectric effect, but it has a threshold that would not be there if light was acting purely like a wave. So if light was acting like a wave, red light, blue light wouldn't matter, you would still get current flowing. But because light is acting like a particle, it is able to knock that electron off like a ballistic electron, boom, and pops it off. And it won't do that unless light is being particle-like and not wave-like. All right, so we're not going to do the clicker question, but what is useful here is this times 10 to the 14th is a frequency that's going to be roughly in the visible range. Right? So photons that are between 700 roughly and 400 nanometers in wavelengths are going to have corresponding frequencies in the times 10 to the 14 hertz. So this is going to be one of our visible-ish wavelengths. It's probably going to be this guy or this guy, and I don't remember which one it is, but it's pretty easy now. Right. So there are lots of different types of spectroscopy. So we've got optical spectroscopy, where the radiation we're looking at is going to be a photon in kind of a visible-ish region. So electromagnetic, we're looking at an electromagnetic wave. So we can look at microwave spectroscopy, UV vis, which we've done, IR, which you've probably done at some point, Raman, which is another vibrational technique similar to IR. NMR is a spectroscopy, flame ionization, atomic emission and absorption, terahertz spectroscopy. The military was really interested in terahertz for a while because those terahertz waves are able to penetrate pretty far into a material. And so the idea with them looking into terahertz was, could we put something on the front of a vehicle that would kind of scan out ahead and be able to penetrate into a container and give us back vibrational information, which we could use to identify explosives or IEDs. So the idea was, you've got something that'll scan up ahead to kind of detect an explosive before you detected it by running into it. You got electron spectroscopy, so Auger. It looks like it's auger, but it's pronounced Auger, just like the drink. EPR, electron paramagnetic resonance. We have an EPR machine up in the lab where the GCMS is, so we might be working on, I'm talking to the guy who runs it and see if we can get one of those working as an experiment. Mass spectrometry, so Fourier transform mass spectrometry, time of flight mass spectrometry, sector field. We did some quadrupole mass spec in lab. So in our optical spectroscopy, which is what we're going to focus on for now, photons are going to interact with atoms and molecules in one of two ways. Right? So you got some matter, and either the light can be absorbed, or you can have some matter that's going to give some photons off. Right? It's either going in or going out. These two types of interactions form the basis for all optical spectroscopy. We are measuring photons, whether we're measuring them going in or we're measuring the ones that don't come back out again. The specifics are all based on the middle. How does the matter react with that light and interact with that light. So here is I love this chart because it is telling you what the matter interaction is for each corresponding wavelength domain of light and what type of spectroscopy tool you're going to use. And it's telling you then what sort of information about that matter you're going to be able to learn. So here is our electromagnetic spectrum. It's going from all the way up to gamma rays, and down here we've got radio waves. They're going from radio waves all the way up to gamma rays. Alas, nobody has yet figured out the gamma rays needed to turn you into a big green monster, but I hear that Bruce Banner's working on it. Like a bumblebee. So the type of matter that you've got, or the matter interaction with the light, is going to determine what wavelength, right, what energy level you're looking at, and it's going to tell you about the type of tools you're going to need. Right? So we're here, this is this very, very small slice of the pie is visible radiation. It goes from roughly 800 nanometers on the low energy end to about 400 nanometers on the high energy end. And what we're looking at is the change in electron distribution. So if you remember back to when we were doing the ICP lab, we were looking at a change from an electron energy level to an excited energy level and then back down again. So if you remember the hydrogen discharge tube we looked at, it was the transition from n equals 6 down to n equals 2 or 5 to 2 or 4 to 2 or 3 to 2. So we were looking at outer shell electrons and energy changes in those. If you look at an inner shell electron change, those are X-rays. If you're looking at a change in nuclear configuration, right? So you're looking at actually how are you redistributing things inside the nucleus, right? You can imagine that's a lot harder to do. That's going to take more energy. Well, those are going to be things in the gamma ray range. If you're looking at a molecular vibration or a motion, so a bending or a stretching or a twisting, that's going to be something that's going to happen in the infrared. The energy of that molecular motion corresponds to an absorbance of light in the infrared. Right? If you go to a change in orientation, so a molecular rotation instead, you're talking about spinning a molecule. And so that's going to happen in the microwave region. That's literally how microwaves work, right? So you've got this oscillating electromagnetic field that's coming in as a photon. Your molecules, your water molecules, are going to have an absorption in that range, in the microwave range. That's going to, oscillate that molecule along with that electromagnetic wave. That electromagnetic wave gets absorbed. That energy goes into spinning that molecule around faster. We observe that increase in kinetic energy as an increase in temperature. And ordinarily, I would stop the class and have us all watch the really, really good video by the engineering guy that talks about how a microwave works. Definitely worth the 8 minutes to go watch that because it's absolutely fascinating. I will post a link to that on Canvas so that you guys can see that. But the discovery of microwaves were absolutely accidental too. So the guy who kind of discovered this microwave effect was working on a radar. So radar also works in the microwave range. And he noticed that a chocolate bar that he had in his pocket, because, why would you just keep pens up there? You got a chocolate bar in there too. So he's like, he noticed that it melted. And he was probably like, oh man, that kind of sucks. Good thing I was wearing a pocket protector, but also, this was a neat phenomenon. And he realized that that could be commercialized into the microwave oven that we now know. The original microwaves were really big, and they were called radar ranges because they used microwave radiation, which was also used in radar. And the real early adopters were cruise ships and ocean liners. because they've got the space to put in a big oven. They have a need to rapidly produce and heat a lot of food at the same time. So they were some of the first big commercial buyers of microwaves. So thanks to the cruise industry, we all have microwaves, which are absolutely fantastic. If you're looking at the change of spin in an electron, that is, you're down to electron spin resonance, or if you're looking at the flipping and orientation of an electron, or then you're looking at something that's, or a nucleus, then you're looking at an NMR, nuclear magnetic resonance. So you're flipping that, flipping those atoms direction around. So yeah, so depending on how much energy it takes to have the matter do a particular thing, you're going to have a corresponding amount of energy in radiation, which is going to have a corresponding wavelength and frequency to it. So when we're doing all of our UV vis, right, we're looking at these inner shell electrons, and it's going to tell us about, or the outer shell electrons, it's going to tell us about electron configuration. So a spectrum is usually a plot of energy, such as intensity or photon count versus wavelength, or frequency or centimeters to the -1, or energy versus mass, or mass to charge ratio for mass spec. It's usually, a spectrum is usually going to have one or more minima, if plotting %T, or maxima. So absorbance peaks or emission, they're called peaks. So we're going to call these guys peaks. The location on the x-axis of a peak, as well as its shape, is it broad, is it narrow, and its intensity, is going to impart information about that matter and light relationship. Right. So we've got a couple of different types of optical spectroscopy: absorption, emission, and scattering. Right. So absorption, that's atomic absorption, UV vis, IR, terahertz. Our eyeballs are basically working on absorption spectroscopy when we see colors. So certain colors get absorbed, and then certain colors get reflected, and we see the colors that are reflected. Emission spectroscopy, so you can have atomic emission, you can have thermal emission, you can have chemiluminescence, bioluminescence, photoluminescence, such as fluorescence or phosphorescence. So if you see something that is glow in the dark, like one of those glow in the darky things, it is probably a fluorescence or phosphorescence process that you're observing. And we'll talk about the mechanics of how fluorescence and phosphorescence works. Or you could do scattering. So scattering is a little bit different. Fluorescence is going to act like a scattering process in that the photons are coming out in all different directions. Raman is a scattering technique where you put a photon, basically you shoot a photon at a molecule, and then you're looking at the photons that bounce back off and any energy changes that occur in that photon matter collision. So let's look at the absorption process. And so light, or electromagnetic radiation, is absorbed by the analyte, and it's going to decrease in intensity. So you put a bunch of photons in, and not as many photons come back out. So there are some general things that are happening here. So the longer the path length, you've got more absorbers, and you got a greater decrease. So if you think about something like a window, you usually think of windows as being pretty darn clear and able to see through. That's why we put them in places, because we want to look outside. But if you take that piece of glass and you rotate it edgewise, and so now you're not looking through the very thin part, you're looking through the length of the sheet of glass. It's not clear anymore, and you can't see stuff, and it might be like a little bit bluish. So if you get a glass stir rod in lab, just pick it up and like turn it sideways and kind of look down it. And that's because it doesn't absorb a lot, but if you put a bunch of those things in the way, you'll start to absorb more light. So the higher the concentration of absorbers, you're going to see a greater decrease. The more molecules you have in that beam, in that light beam, the harder it is to see. That's why it's difficult to scuba dive in a swamp, right? Because you've got all of the dirt and all of the tannins and all the things that are in the water that are absorbing light. And so it's hard to see down at the bottom of the muddy lake. So basically, the absorbance process is photons go in, only some of them come out, and we can measure the ratio between the photons that make it out and the number of photons we put in, and we call this the transmittance. Our absorbance is just going to be the minus base 10 log of transmittance. So our absorbance is how many of them didn't make it out. And we're going to put this into a log type of scale, right? So we've got transmittance, which is on a linear scale, and then absorbance, which is on a log scale. And so you could think of absorbance as like being P transmittance, right? So it's just another one of these minus base 10 log P functions. And so here is what's happening in a lot of these, processes where we've got some sort of ground state. In this case, they're doing it as an electronic state. And then a photon is going to, in the case of an electronic or UV vis, it's going to take an electron from a ground state into an excited state. So the energy went into exciting that electron, right? So our energy is still being conserved, and it's just that it's not existing as a photon anymore. It is now imparting that energy to exciting an electron from a ground state into an excited state. Right? Sometimes you can get a photon with a little bit higher energy, and you can go from the ground state into an even higher energy state, a higher N level. So here you've got a change in energy 1, and here you've got a change in energy 2. And you need 2 different frequencies of light because these energies that for the excited states are different. When you plot this guy out as an absorbance spectrum, so if you look at all of the different possible wavelengths of light that are coming in, right, if you don't have the right energy, right, and you can't make it up to here, you're lower. Hold on, we kind of lost Zoom for a second there. Share screen. Okay. Should be good. Okay, so what I'm saying is that if you start off with like red light, and then you're going to higher and higher energy, and you're not going to absorb anything, and then you get to this energy level, and boom, you start to lose your photons. They're able to excite that, and then you go to higher and higher energy photons, bluer and bluer, and then boom, they're able to get into here, and they will get absorbed once they have sufficient energy to reach the second energy level. So what you will see is that you got this little peak here, right? This little peak here at high energy. This is an energy axis. No, it's a wavelength axis. So our short wavelengths, right, our bluer wavelengths here are higher energy, right? They are less likely to undergo this transition than these guys over here. So generally, your higher energy peaks are going to be smaller than your lower energy peaks. Okay. The size of the arrows here, which is representing the difference in energy levels. All right, so let's take a look at this figure. It's called the Jabonsky diagram. What it's showing is that you've got IR, infrared, visible, and ultraviolet. And for you to do ultraviolet, to absorb an ultraviolet photon, right, those are pretty high energy. So when you undergo ultraviolet absorption, you're going from a ground state up into a pretty high energetic state. If you're looking at something that's in the infrared, an infrared absorption, you're really just kind of moving that a little bit. So the size of these arrows is going to be proportional to the amount of the energy. And these E0, E1, and E2 are representing different electronic energy levels. And these sublevels over here, right? So these E's, are big bold lines, are representing electronic states. And these thinner lines on the right-hand side, 1, 0, 1, 2, 3, and 4 are representing different vibrational states of those molecules. So our IR spectrum is moving from one vibrational state to another, whereas something that is going to be a visible transition is going from one electronic state to another electronic state, and maybe up to another electronic state with a little bit of vibrational energy, which we wouldn't see because that'd be IR. So this is what a fairly complicated UV vis spectrum looks like. This one is for potassium permanganate, and you've got a couple of different little peaks here, 1, 2, 3, 4, and you can see that as you increase the concentration of the potassium permanganate, those peaks get higher and higher because you're starting to absorb more and more stuff. Right? So the taller the peak, the fewer the photons get through. So this guy's going to absorb stuff in the range of 500 to 600. So that's covering roughly orange, yellow, and green. So it's absorbing a lot of green stuff, which means that the colors get through are red and blue. And so if you see red and blue make which color? Purple, right? And so potassium permanganate, excuse me, has a very characteristic deep purple color to it. And if you guys remind me in lab, we will try to set some potassium permanganate on fire, okay? So one of the other things that you will see is that that spectrum may change based on what solvent you are working on. So if we've got our molecule and we look at it in aqueous solution, we may get like a big blob. But if we put that into hexane, right, we're going to start to see some peaks. Sorry, I'm having killer allergies today. And if we put that again into the vapor phase, and we look at it as just a gas molecule, we're going to get lots more structure out. So what's happening here is an effect called solvent or collisional broadening. And if you have just the molecule by itself in the gas phase, gases are pretty far separated from each other. And so there's not really going to be an interaction between one molecule and another. Right? And so you're able to get the spectrum that really accurately shows these electronic transitions. If you put that guy into solution, now these molecules are starting to bump into each other. And when they do that, some of that energy of that can go into moving a molecule and smashing it into another molecule. And so these energy levels here become broader and less distinct. We now put this guy into an aqueous solution where there's hydrogen bonding that can happen. And hydrogen bonds are so variable, right? So you've got some, you know, they interact over large ranges. They're not well defined. They're not exactly a very strong bond between your solvent and your analyte. And you end up with these very poorly defined transitions where you see that as a very broad continuum looking version of these peaks kind of blending into each other. And so the peaks get broader and broader and broader as you move them into aqueous solution. And that's, again, because of this collisional broadening that happens, or the fact that you've got the hydrogen bonding that happens. So to help define what's going on with this, if you look at each of these peaks, right, this molecule is going to absorb different number of photons at different wavelengths, right? So remember, our spectrum is a function of absorbance versus wavelengths. So at different wavelengths, we're going to have different molar absorptivities for our molecule. So our molecule is going to absorb different amounts of light at different wavelengths, and we call that the molar absorptivity. And they're going to range from about 0 to 10 to the 5th in our UV vis region. So our maximum extinction coefficient or molar absorptivity is going to be about ×10⁻³ for some weak bonds and or less, and 10 to the 4th and up for something that's a strong absorber. Electrons involved in chemical bonds are going to be the ones that absorb energy in that UV vis region. And some non-bonding electrons are going to as well. So we will go, for those of you who are in inorganic or PChem, you're going to look at this and go, oh, wow, this is way oversimplified. For those of you who have not had this, it might be a little bit over your head, but that's okay. You might remember some of this from Gen Chem when we talked about MO theory, molecular orbital theory. So if you were looking at the sigma to sigma star transition, that's going to occur in single bonds only. These are sigma bonds, those are primary bonds, and they're going to be in the deep UV region. Right? So if you're going to see an absorbance for that single bond, it's going to be in the UV. That's a pretty strong bond. If you need to excite something in there, it's going to be pretty high energy. And that's going to be about 135 nanometers. That's pretty short. Your pi to pi star, so that's your bonding to your anti-bonding. Right? So you can go from a lower energy pi orbital to a higher energy pi star orbital. Those are most probable transitions for organic molecules, and for chromophores in the 200 to 700 nanometer region. So you're able to see some of these. So if you're looking at beta carotene, for example, it's going to have an absorbance in this region. These are very large extinction coefficients, so 10 to the third to 10 to the fifth, and you're going to have very, very few solvent effects. I think your solvent effects are going to be minor. If you are looking at an N to a sigma star, so a non-bonding up into an anti-bonding sigma orbital, those are going to occur in saturated molecules containing unpaired electrons in the 150 to 200 and you'll see them in the 150 to 200 nanometer range. They're going to have an extinction coefficient that's small, 10 to the 2, 10 to the third, so you're not going to get a very strong absorbance, and those solvent effects are pretty big. So if you think about what's happening, here is this poor electron, it's just kind of sitting out there as a non-bonded electron on the outside of this molecule, minding its own business. It's able to interact with that solvent a lot more strongly than this sigma bonded electron or this electron that was already in a pi bond. So this is this unbonded electron. Yeah, it's going to have an effect. That solvent is going to affect that, and especially if you're going to then try to put it into a sigma antibonding orbital. You can go from a non-bonding into a pi star. So it's similar to that pi to pi star transition, but it's a lot weaker absorptivity. You've got a lot stronger solvent effects, just like we saw with the N to sigma star transition. We got big solvent effects. So the part of a molecule responsible for light is called the chromophore, and that means chromo from color. Any substance that absorbs visible light when light appears colored when white light is transmitted through it or reflected from it. White light contains all the colors of our visible spectrum, and our eyes detect the wavelengths that are not absorbed. The absorbed color is called the complement of the absorbed color. So what we see is kind of the opposite. We call it the complement. And so if you are absorbing a maximum up here in 380 to 420, your absorbed color is going to be violet, and the color that you will observe is green. If you are absorbing 470 to 500, you're absorbing blue photons, and the color that you observe is red. If you are absorbing photons that are 680 to 780, you're absorbing red photons, and the color that you see is green or blue-green. Right? So where do you see this? If you drive down the road and you are looking at an old sign and the colors are starting to fade, what you will observe is that those blue colors, the blues, the greens, and the purples, tend to stay around a lot longer than the yellows and the oranges and the reds do. So you'll see those red colors fading faster. And the reason why they're fading faster is because they're photodecomposing. So sometimes you slam that photon in and you excite the electron, and rather than now you've got more energy in there in that molecule, and sometimes it just falls apart. You've got too much energy to hold itself together. And so you can undergo photodecomposition, and that is more likely to happen if you absorb more energy. And these 400 nanometer photons have more energy than these 800 nanometer photons. And so our things that are colored blue are absorbing less energy than our things that are colored red. And so these red guys are absorbing blue high energy light. You can make yourself a little spectrometer if you want. We will be doing this in PChem or some variation of this next semester. So if you're in PChem, we get to make our own spectrometer. We may or may not do it this way, but basically all you're doing is you're taking a box, you're letting light in one part. It's going to encounter a transmission grating, which will spread the light out into its different wavelengths. And then you can take a picture of it with your smartphone. When you do that, and you're going to see if you've got white light through there, you're going to see the full rainbow. If you put in potassium chromate or dichromate, right, you're going to absorb some blue light and you'll let some green and yellow and red through. Your rhodamine 6G is going to let some blue and some red, but leave off some of these greens and light blues. Your phenolphthalein, which is pink, is going to let through a lot of red and some blue. And your bromophenol blue is going to let through some green and red. So you can compare the absorption spectrum recorded with the spectrophotometer and with the visible spectrum collected with a papercraft smartphone, right, for dichromate. And you can say, well, does the absorbance peak represent colors that are lost in the transmitted visible spectrum or colors that persist? Right, so here's our dichromate. Right, this is our actual, we did it on a machine. Right, we did it on a machine. Here is our dichromate over here. And so these things that have high absorbance are the colors that are not getting through. Okay. And then here's our absorbance for phenolphthalein in pink, right? And it's missing these guys kind of in the middle. Compare the absorption spectrum recorded with our camera versus our spectrum for phenolphthalein. And what we see is that, yes, the phenolphthalein absorbance is cutting these guys out and we're letting through the red gets through, the blue over here, the blue gets through. That's these guys in the middle that are getting lost. And you can do the same thing with any of the other compounds. Now the difference being that when they've got this, right, and they're taking a picture with the camera, this is very, very qualitative, isn't it? Right. This over here, right, they have used a spectrometer to measure the amount of photons that are getting through rather than just very qualitatively doing it with a camera. Now, can you quantitate something like this, right? Because obviously there's photons coming through. They've collected them with the camera. Can you then quantitate and say, well, how many photons of a particular wavelength in the red, or how many photons over here are blue? And the answer is yes, you can. And there are spectrometers that work in exactly this way. And so instead of generating a picture that we can see with our eyes, they will just take that data and they will, rather than filtering it out and making it into an RGB color, they will turn that directly into intensity information, which you can quantitate. And this brings us to Beerus Law. So you have come across Beerus Law before if you've done the EVVis lab. You have come across Beerus Law if you've ever had a thing of Kool-Aid at a church picnic and you're like, what kind of weak McDonald's level of orange drink is this? And could you put some more flavoring in here? Because this is going to be rather unsavory. So Beerus Law is just saying that our absorbance in a solution is going to be related to the path length of the thing we're looking at. So like that sheet of glass one way versus the other way, and how many absorbers are going to be in that path length. That's going to be related to the concentration of the number in there. So if I increase my concentration, I can get more absorbers in there. I'm going to increase the absorbance of my sample. It's going to be related to the path length, like we said, and then it's also going to be related to the extinction coefficient at a particular wavelength. So Beerus Law is a way that ties in something that is inherent to the molecule, its extinction coefficient, or molar absorptivity. It's related to the path length, right? And we will design instrumentation to keep our path length constant and reproducible. And then concentration, how much stuff do we have? And so Beerus Law is a nice way for us to relate absorbance, which is pretty easy for us to measure, and concentration. And Analytical chemistry wants to answer two questions, right? What do I have and how much? Concentration is how much. And so Beerus Law gives us quantitative information about a sample. So if we know what the absorptivity is and we know what the path length is, that's usually set up by our instrument, we can figure out what the concentration is. Right? So yeah, you could look this up. Oftentimes there's tables of these things that you can figure out what the extinction coefficient is, or you just run a standard or calibration curve. So if you remember, our transmittance or percent transmittance is going to be the number of photons that we get out divided by the number of photons we put in. Our absorbance is just going to be the minus base 10 log of that. Our Beerus Law says that our absorbance is going to be proportional to the extinction coefficient times the path length times the concentration, which means we can rearrange that and say our concentration is going to be our absorbance divided by our absorptivity and our path length. There are some assumptions that are going to go into Beerus Law. Assumption number one is that you are dealing with monochromatic light. You don't want two different wavelengths of light in at the same time because things may not necessarily absorb the same at two different wavelengths. You are assuming that you've got parallel or collimated light. So you don't want the light going, you want it all straight and parallel. You won't assume that the solution concentration is not too high or too low. So remember, this guy is absorbance is going to be a log function. So if you have like a very, very high concentration, you're looking at basically no photons getting through. On the other hand, if you've got a very, very low concentration, it might be hard to pick that up, right? So you've got a whole bunch of photons coming through and billions of photons, and like it dropped a little bit. Might be very hard to pick that up. You are assuming uniform sample distribution, so not like red on the top and blue on the bottom. Right? It's got to be evenly distributed. You are assuming a uniform sample path. Right? So if you're looking through one thing, it can't be like, you know, thick cell on one spot and a thin cell on the other spot. And so you're assuming that that sample path length is that you're working with straight, uniform cells of the same size that you're putting your sample in. You're assuming that you don't have any reflections or stray light, so no reflections, so nothing going in and then either bouncing off and you don't see it, right? It's a photon that gets lost and recorded as an absorber, but it's not really. You're assuming that you've got no stray light coming in, so light from the outside isn't coming in and looking at and being detected by your detector and saying, oh, look, there's not an absorber in there when there really is. You're also assuming that no fluorescence is happening. Right? So if you put a photon in and it gets absorbed by a molecule and it fluoresces, that fluorescence goes in all different directions, which wouldn't be a problem, but some of those photons are going to go and fluoresce towards the detector. And usually our detectors are colorblind and they will not know the difference between a photon that was absorbed and then re-emitted as a fluorescence photon and one that was just not absorbed at all. And so fluorescence will make our solution look artificially low in its concentration. So excuse me, this would be a nice quiz or test question, you know, kind of explain through all of these things. So, you know, maybe if I were living my life, I would go through and I would list this out and then kind of do an example and say, oh, is this going to make my concentration higher or lower? What sort of error do I have with it? Let's look at our polychromatic light. So if we got this, right, and this is our absorbance as a function of wavelengths, and this is our full spectrum, and we're putting in photons from both here and here, right? If we're looking at an ideal Beerus Law, it should be a nice straight line. But if we're throwing in some sneaky photons from over here, where there's less absorbance, right, we're going to see a deviation where we've got what looks like a lower concentration. Right? So in other words, we're trying to measure at lambda max. We've got some other light coming in that isn't going to be as efficiently absorbed in band B. And so this is band A, not B and A and band B, not B and B. So we've got some stuff coming over here in band B, and it's sneaking in, and our absorbance looks lower because now the number of photons that we collect versus the photons we put in, we're getting more photons out, right? Because we get some of these B photons in. And so it looks like our absorbance is lower than it actually is. And so you want to work this guy at just lambda max. You could do it over here at just B, right? Just wavelength B. You would still get a straight line, but it would be a straight line that would be less intense. And if you're blending them together, A and B kind of blend together, and you end up with this kind of curvy line, and it's not linear. So that's bad. Yep. When you are running your spectrometer, you want to run a blank to get an accurate measurement, because you are physically taking a container that is itself going to interact with the photons that you're putting through your instrument. So you got to use a blank for your accurate measurements and see, well, if I've got nothing in there that is absorbing, what is happening if I've just got nothing? So you can have reflection losses at an interface on the front end. You can have some reflection losses at the inside. You can have some scattering losses in your solution. So things are going to scatter photons as well. Some things are going to scatter photons better than others. So your emergent beam might be a little bit dimmer because you had some dust in there that was scattering the light in different directions. And so you've got reflection, you've got some scattering that could happen, right? This could just be losses in photons that are there because you've got this physical container. And if you think about that, it makes sense, right? If you had no photon losses on your sample holder, on your cuvette, then you would not be able to see your cuvette and it would be invisible. So you've got to have some photons that are either appearing or bending or getting redirected towards your eyeballs in order for you to see that physical cuvette, which means there have to be some sort of photon losses. You do that blank so you can account for those losses and normalize your absorbance to account for that loss of photons that happens because you can see your cuvette because it's not made out of air. So here's an example of doing some Beerus Law. We've got trace amounts of iron in drinking water, and you're going to form, say, complex of iron with phenanthrylene. If your standard concentration contains 5.63 times 10 to the minus 6 molar iron, exhibits a transmittance of 76%. In a 2 centimeter cell at 510 nanometers, what's the absorbance of this solution and the molar absorptivity for the complex? So the first thing you do is you've got your percent T, right? And you're going to convert that into transmittance out of percent transmittance. So you do minus the base 10 log of 0.76 to get your absorbance, 0.119. Right? You then throw in your Beerus Law that says your absorbance, 0.119, is equal to the extinction coefficient times your path length, which is 2 centimeters, times your concentration, which they said was 5.35 times 10 to the minus 6 molar. You then compute epsilon, 1.1 times 10 to the fourth. And then the units are going to be per molar per centimeter, right? Or liters per moles centimeter. A 20 milliliter aliquot of drinking water containing our iron 3+ and iron 2+ is titrated with hydroquinone to reduce all the dissolved iron from O-phenanthrophenone to all of it to iron 2+. You add in the phenanthroline and then you dilute it again. The absorbance inside our cell is 0.085 at 510 nanometers. How much iron was in that water, and figure that out as ppm. Okay. So the epsilon value determines the extent and magnitude of the absorption. It's going to be 8.7 times 10 to the 19th times the transition probability. Oh man, these in the wrong spot. Times the transmission probability, where you got a P1, a P less than 0.1 is a weak or forbidden transition. If it's between 0.1 and 1, it's a strong or allowed transition. And A is the cross-sectional target area of the molecule. I'm sorry, this we would want to have there. Our epsilon values are going to be ranging from 10 to the minus 5 in the UV region, and we already saw that it was some non-bonding electrons do this, but it's mostly going to be bondings. And if you are working in a mixture, our absorbances are going to be additive. So our absorbance at a particular wavelength is going to be the sum of the absorbances at that wavelength for component 1 and the absorbance at that wavelength for component 2, and so on. So you can expand that and say that your overall absorbance is going to be the concentration of whatever thing 1 is and its absorptivity, and the concentration of whatever component 2 is and its absorptivity. So if you take yellow and blue and you mix them together, you end up with green, because both the yellow and the blue are going to absorb. And you're going to have some overlap between them. And I will stop here because this is actually a pretty complicated example to go through. But we'll do analysis of mixture next time. Do you guys have any other questions? Is anybody going to stay on afterwards and ask questions?
I just have a quick question.
Yes, sir.
What homework corresponds to this? Because I checked chapter 24 and it's mostly gas chromatography.
Yeah, 24 is going to be chromatography, and I probably need to push that back. So let me get back to you, and I will put an announcement on there about the homework and what ones you should do next. We are probably not going to get to that. Honestly, we're probably not going to get to some of those chromatography questions.
Okay.
But anybody else? So I'll check the homework due dates and announcement. I think we're close enough to where I can finalize like what's gonna be due when and what's gonna be reasonable. And you know, if you guys want to do those other ones, great, but I'm not gonna require them or count them, if that's okay. So I will probably, how many people want me to keep those homework assignments on there? Well, I'll make a little poll, but I'll see if people just want me to just straight up cut those out, or if they want them to practice on. But
I don't know if this is an option, and it might not be, but like, is there a way to just like delete them off Canvas and keep them on?
Yeah,
I don't know if that's
I can do that. It's if you want them on there to practice, then yeah, I'll leave them up there that you can practice. So I can leave them on there. That's what I'll do. Okay. I mean, that's kind of my feeling, and that's what I would have wanted, is like, I want to be able to practice, because questions like that might come up on an exam. So we will do some exam review, hopefully, in the last class or two before the final, because I think that would be important to do. So it'll be like just one gigantic office hour the last day of class. Okay, so.
And then I have another question. This is just about the final, which I know we've talked about a lot, but like, I think we have 2 hours like in the window, like for that time period. And normally, like, I know like it's not normal for us to have an hour and 30 minutes for our quizzes, but I guess like you probably don't have this planned, but like, how will that work with timing and everything for the final?
So we have a certain amount of time for the final, and I will give everybody the maximum amount of time for the final. And then for the people who have accommodations, they will get whatever that maximum amount of time is extended to theirs. I want to say it's like 2 hours, not an hour and a half, but I could be wrong. So, you know, I will try to write the exam to take an hour and a half and then give you guys 2 hours. I have no idea how many questions it'll be. You know, I'm thinking maybe 20 multiple choice questions tops, 5 questions in the concepts, and then maybe 10 questions, or, you know, and then maybe 10 questions that are in problem solving, maybe less. I don't know. I mean, because given like, let's say it takes you 10 minutes to do a problem solving question. You know, if I give you 5 of those, that's almost an hour right there. So make formula sheet.
Does that mean we're not having short answers? You might have said that.
Yeah, no,
I
I'll
don't
do a
know
short
if
answer section too. It's just that that short answer section is usually a smaller part. You know, and I might do more short answers, less problem solving. I don't know. I will try to make it as balanced and doable in an hour and a half as possible. So that's going to be tricky to do. But I will also try to do it roughly evenly distributed throughout the entire course content, so that we'll have, you know, some stuff from the beginning chapters and some stuff from the later chapters. Yes, and so I'm going to, the way we'll do it is there'll be a quiz that'll be set up in Canvas. That'll be the multiple choice. And then it will be an assignment where you will upload your answers to the, so you'll basically scan and upload your answers to the written part. That make sense? So we'll have, okay, cool. So yeah, 2 basic sections. The multiple choice will be its own, and I'll set that up as a quiz in Canvas. The submissions will come through an assignment, so you'll have to practice scanning stuff with your phone or a scanner. No, the multiple choice will be set up as a quiz. So it'll be 2 different things we'll need to access, and I'll have them open at the same time. My suggestion would be, because it's set up that way, to do the multiple choice part second, so that you're doing your problem solving and your short answers first, because 1, that's probably going to be where most of the points are, and 2, you know, if you do run out of time, then you can always guess on multiple choice, but you'd never want to turn something in that's blank on problem solving. So kind of work the test backwards. Can you submit scanned work for the multiple choice? Oh, so like if you're working through your multiple choice and you want to take notes and have an explanation for that, yeah, go ahead and do that. So like if you're working through your multiple choice thing and you've got some work you wanted to show me on that, yeah, or reasoning behind why you picked a particular thing, and then, you know, if you think that you got that question wrong unfairly and you wanted to talk about it, then yeah, that's fine. Because I'm not a big fan of multiple choice questions for exactly that reason. It's like, well, my reasoning is this, and that's why I picked this answer, and it was, you know, some poorly worded question on my part. Then yeah, make your case and write that down and submit that. Okay.
Following up on what you just said.
What?
Sorry, just following up with what you just said about the multiple choice, and like we won't be able to see what we got wrong, I guess, like if it's set up like
no, it won't tell you which ones you got wrong, but you'll have a good sense of like, you know, I was really nervous about this one. Could you check this? And you could write that on your thing, and then I can check it. Like, you know,
okay.
You'll know the ones that you feel a little sketch on. And just say like, Star, could you please look over multiple choice question 5, because I think blah, blah, blah. Okay? And then that's, so in terms of like what kind of questions you would see in multiple choice, like one of those convert wavelengths to a frequency, or frequency to a wavelength. That's a multiple choice question. Doing something with Beerus Law that might be a little bit more involved, that would be a problem solving, or something else that wouldn't necessarily be a super duper quick computation. Maybe it was a real easy Beerus Law and I gave you all of the things and you just had to do it. But something like we're going to do with analysis of a mixture, no, that's not a multiple choice question. Okay, cool. Anyone have other questions?
Is it okay if I stay after?
Yes.
Okay,
Yeah, so
thanks.
why don't you hop on over to, because I've got to, so give yourself like 5 minutes. I'm gonna hop over to the, I've got to close this down, save the file, and then I'll meet you over in the office hours link, if that's okay.
Yeah, thank you.
Okay, yeah, give me like a couple of minutes because Zoom's got to like compress and save all the stuff so I can upload it. So get yourself a coffee, go to the bathroom, watch another set of commercials and YouTube videos. All right, whatever to kill 5 minutes, but I will see you there in 5. All right. Otherwise, I'll see you guys on Thursday.